Okay, everybody, thanks for being here. How's it going? Yeah?
Pretty good.
Pretty good? All right, got some enthusiasm from Quadrant 1. What's up? Okay. How did the airfoil stuff go?
Fine.
Fine? Okay, thanks. Is did you have issues with importing? Do you have issues? No, just did it work? That's good. Some people did have some issues. I'm not quite sure exactly where, but it can be tricky. And I know that when I try to do it like just by memory, or it's very difficult to do the whole thing. So okay, well, good. I'm glad it was working for you. I guess it's one of those things where you're kind of preaching to the choir. The people who are in class right after the assignment is due might be the ones that were able to get it done. If there are questions, though, please feel free to stop by the office during office hours. They are, again, Tuesdays, 12:30 to 1:30, and Thursdays, 3:45 to 4:05. I guess somewhat surprisingly, my office hours were a little bit empty today. Someone came in, but it wasn't about the class. So just, but in the past, we've had a lot of people, or a few people. So just, I guess, it ebbs and flows. All right. Well, anyway, today we're going to talk about structural mechanics, and the assignment that will be due for this particular topic, which is going to be a little bit of structural mechanics plus a little bit of impact analysis from our days doing design mechanical components. Goes to the impact equation. Maybe some of you already done this assignment. Do you want to go ahead? Yeah. Okay. All right. Good. This one is going to be due Thursday at 4 p.m. And unlike the last couple, we kind of combined lab and post-lab and made them do later. This is just the lab. So you'll be able to rest a little bit easier not having that post-lab. Of course, everyone is going along, working on their final projects, and I'm happy to talk to people about their final projects during office hours if you have questions. The next checkpoint, though, that's coming up is, I believe, due on April 18th. I have to check my checkpoint, and that one is going to be on convergence. So that one is, we're ramping up, getting more and more detailed, more and more committed to the particular project we're going to be doing. Any questions administratively? Thank you for being here. We're going to review mechanics, and we've already kind of reviewed mechanics a little bit, but now we're really going to review mechanics for the sake of structural mechanics. And we'll discuss the pillars that we have based our efforts in mechanics and materials pursuing, and how they relate kind of, again, in an impressionist perspective over finite element. Finite element of mechanical problems, again, could be a whole class in the books, all right, in theory. And we're just getting to touch on the tippy top of the mechanics. I think I've mentioned it before. I did take one class of finite element analysis where we focused on mechanical problems, and we did things, it's not because I was just old, or not because I'm just, from a slightly different generation. It's also because we had to do the analysis. So you have the exams, and you have to write out what's going on with the elements and that stuff. And I had to definitely go back and look at the textbooks to remember all those details. But there are textbooks out there that go through how to apply finite element analysis to mechanical problems. We also did do computer simulation, though. It wasn't that way. We'll discuss some blasts from the past, again, mechanics, materials, plane stress, plane strain, and how we think about these simulations, or simulations of these types of setups. And then we'll get into some Ansys examples and do some of the same things that we did in mechanics and materials using pre-pro max and calculus, do them in Ansys. And that will be kind of a springboard to dive into the assignment, which includes the diving board. Okay? So, here we go. We really care about internal stresses, internal traction vectors, internal loads. And we can become like those engineers that think about invisible things, right? Usually in mechanical engineering, we probably have a little bit more affinity for tangible systems. They break, you get in trouble, and it seems obvious in retrospect. But in reality, it's because we may have unanticipated circumstances, or I guess, or a fault, or just didn't quite understand what's happening inside the object. So inside the object of our liking or analysis, we end up looking at these forces, these internal forces that are keeping things in equilibrium that might be acting on small areas. And these delta forces, these small forces over these small areas, are what we call traction vectors. And then as we get into describing these traction vectors, as you know, we can think of the coefficients on the direction vectors for the traction vectors as our lovely stresses. Okay? So here you go. Okay? And we define these stresses as being on a surface and in a direction. Okay? So in this case, we were talking about a bunch of stresses on the z face of this whatever object, or this plane is the z-plane, okay? And we're looking at the coefficients, or we're looking at directions of stress in the x, y, z directions. So the convention, of course, we've already discussed because we've done some fluid mechanics, and in fluid mechanics, often we're very concerned about what's happening with shear. We're also concerned about what happens hydrostatically with pressures, but shear becomes more the thing that we're considering. And in mechanics, we do both, right? We're thinking about the normal stresses, and we're thinking about the shear stresses. We're thinking about the effective stress. What is that material seeing? And then comparing these loads, these stresses, to failure criteria that we might be interested in pursuing, or try to understand whether or not something is going to fail. Yes, another aside. Stress, these stresses form a stress tensor. This is a 3D description of things. Do not say sigma ijk. That does not work. That does not make sense, right? Because each one of these things is on a face that's given by an index in 3 directions, and then we have the second subscript, which is giving us the direction the stress itself is actually acting in those 3 directions. Okay, so shear stress, right? We've talked about this before, and if we want to go back and do this in a more slower fashion, more involved, or just look at the slides which are available, you can get this idea that you have to satisfy equilibrium, otherwise these elements would start rotating or accelerating with the angular acceleration of the elements. That would be not statics. Okay, and we also know that once you have kind of one of these arrows of a shear stress drawn on to the element, then you can draw the other ones. Okay, because we satisfy both the moment and the force. Okay. Again, we're going through this pretty quickly, and it's just kind of review. When you have 3D, you can make a nice little element, and this one only has the shear stresses depicted here. Okay, the normal stresses would be coming out of the faces of this cube. All right. We can also use tensors, and we can use the Cauchy kind of nomenclature to describe them. You can also come up with ways of using rotation matrices to be able to rotate these boxes in the state of stress about whichever kind of coordinate direction we want, or we can combine them to have multiple rotations. Essentially, use rotations. You can describe the stress in a useful coordinate system, and you can figure out whether or not these flows would contribute to failure. It's also, of course, the stresses do end up giving us an idea of how we can think of strains. So these strains then will extend. Essentially integrate these strains, you will be able to get the deflection or the deformation of the object in question. Okay, so that's like a very brief overview of things that we remember. Okay, and I guess I have a couple things here that I can kind of. So let's see. I don't know if I can subtract them or not. Let's see if we can. Yeah, why not? Let's just get rid of these because of that. Okay, and we'll go back to this. Okay, so what? Now, question for you all. What are your favorite material properties for structure, for solids? What are your favorite material properties? Yes?
Normal stress.
Okay, that would be a quantity that we are concerned about, all right? So yes, my tendency is give me the normal stresses and I'm a happier person. Asking about material properties though. Yeah.
Elastic modulus.
Elastic modulus. Okay, why do you like the elastic modulus?
I feel like it's a pretty, uncomplicated quantity. I feel like, we got it, we lose it.
Okay, all right, that's confidence. That's confidence. I like it. Professor Singer has told his students you can think of many things as springs. I agree, you can think of many things as springs. The elastic modulus is a nice way to kind of get an idea of what the stiffness would be, well, for the element, at the element level, but also once you start building structures. Now, you've taken TMC, right? Design mechanical components. Coil springs, what actually determines the stretchiness of them? Do you remember? Is it the elastic modulus? Is it something else? Because we're talking about elastic modulus and springiness. This is just for your good to know. You don't remember. Okay, that's okay. All right. What was the interesting thing about the coils? We're talking about the helical coils. How did he figure out if they were going to fail or not? Was it looking at a normal stress? Was it looking at a shear stress? So it's good to we're just going to review mechanics system. We're gonna spend some time in Ansys land, right? And we're gonna put all this stuff in there. And when we say, hey, yeah, we want to compare against ground truth, that's when we say, oh yes, I remember I took a mechanics and materials class that was awesome at Rutgers. Just kidding. All right. No, so do you have an idea? What is a helical coil really like? Is that helpful? My hands? Yes. Yeah, it's kind of just like a torsion bar that's been wrapped around. Okay? Except the way you kind of think about it is not like this. You think of it more as, okay, I've got a force and then it's off-centered from the side of the coil, remember that? And then you have these torques being applied, right, along it. And then you have the shear stress. So the shear stress actually ends up being what you're concerned about, failure. And where is the shear stress the highest? On a cylindrical object? At the surface, right? Right? Remember TC over J? Or TCNJ, right? Our friends in New Jersey. Okay, TCNJ. Okay, so yeah, we end up we care about the shear stress and the shear modulus when we think about the stiffness. Now, back to the question. If I care about the shear modulus, does that mean I care about the elastic modulus? Yes, I agree with you. Good quadrant one. How is the shear modulus related to the elastic modulus? Yes.
It's just the equation. I think it's
Yeah. All right. Good. Okay. So it's actually the equation I erased just a couple of seconds ago, right? What's your name? Alex. I've asked that before, haven't I? Yeah. Okay. I'll remember one day. Yeah. Just keep answering questions, and then we'll be in good shape. So right. So as Alex was saying, we can relate the elastic modulus to the, or we can relate the shear modulus to the elastic modulus. And what's another interesting material property that comes up in that equation that I just wrote? Quadrant 2. What's up? How are you doing in quadrant 2? So what is the material property of question? Nice job not sitting in quadrant 2 when I was asking them questions. That's good. Good job walking in quadrant 1. Okay, quadrant 2. So what is this quantity of interest here in the equation? What did you say? Or was that a radio? I heard something. You see this little squiggly, like V-like thing, right? That's a nu. What's that material property? So interesting. So important. You're gonna know about quadrant 2, even though you're kind of in quadrant 3, but that's okay. Go ahead. Yeah, it's the Poisson's ratio, right? Okay? And what is the Poisson's ratio? Yeah, so you just got it, right? It's the negative of it, right? But it's the negative of the lateral strain over the longitudinal strain, right? Now, when you start doing your mechanics problems, do you think you're going to put, or which material properties do you remember which material properties were really important for doing your finite element analysis? Any of them? Were these two parts, did you put these in? Yes, we did, right? Okay? And so we'll see that the Poisson ratio, right, that effect, when you apply strain in one direction and you get, or you apply tensile strain, right, of extension in one direction, you get contraction in the two orthogonal directions, that will play out in the simulations that we do. Okay? So usually at a bare minimum when you start doing your mechanics materials types of simulations, you're going to put in an elastic modulus of Poisson's ratio. They'll also typically ask you for a density, okay? Even though that may not have an effect on the actual system that you're using. Okay, but you have some type of mass associated with the structure. Now, the things that we will be measuring, right? This is where Alex was so excited about normal stress. Okay, we're looking at the normal stress within the object. We're looking at shear stresses within the object. We're looking at normal strains within the object. We're looking at shear stresses within the object. Okay, or shear strains. Did I say that? Why do we care? So I've got essentially this whole structure, and now I've got a whole bunch of tensors, like at every element, at every node. Okay? And I've got all this information. Why do we care? Well, we care because we want to figure out whether or not we're going to fail, how we compare to another very important material property, which is strength. Now, strength, we think of tensile strength, we think of ultimate tensile strength, we think of shear strength. Strength is usually just one quantity, though. And often we like the tensile strength, right? Someone has pulled a sample for us, we know what the stress is when it kind of begins to yield, at least both for ductile and brittle materials, but in particular the ductile materials. Right, we got that nice yield, we go into the plastic regime. Okay. We typically don't actually put the yield strength into our finite element analysis, at least not for the simple stuff. Okay, there are more complex models that you can use, and Ansys has them. But if we're thinking about our linear elastic, perfectly plastic models, okay, we actually don't really use, we don't put the yield strength in there. This means that finite element will just keep cranking up the numbers, okay? And so if you're not kind of looking for some type of value that crosses the threshold of going into plastic, the plasticity, you are going to be essentially creating garbage. And so we want to try to avoid that. And so for our analyses, mostly in this class at least, we're going to be focusing on the linear elastic regime, which is what we typically have done all this time. I mean, we talk a little bit about, well, we're going to talk about failure criteria in a minute, actually. How do you go about, though, you got these beautiful tensors, or these, and that's just a fancy way, technical jargon of saying you got a sigma x, sigma y, sigma z, tau x, y, tau y, z, tau x, z, right? Okay, more jargon for you. Okay, that's why sometimes we teach something, right? Teach jargon. No, but how do you go about if someone gives you boomba? Here's your state of stress. I give you 6 components of stress. How do you go about figuring out if it's going to if you're going to yield? Any ideas? Yes, Alex. All right, Alex, go quadrant 1 today. All right, represented.
Doesn't a material just have like an ultimate strength or fracture strength, so don't you just need to know that?
Well, yeah, but I'm not telling. Yes, it does. So there's this other material. There's this material property strength, right? Some type of yield strength, maybe, or maybe it's a shear strength, right? But I just gave you this tensor, 6 values. How in the world do I know if I'm going to fail?
Von Mises.
Yeah, that's a good one, right? When is von Mises applicable? To what types of materials? That was your name is? Andrew, all right. Okay, so Andrew, do you remember there were kind of 2 classes of materials we've discussed in our mechanics and materials world? What are those 2 classes of materials? Okay, quadrant 2 in the house, all right.
Brittle and ductile.
Yeah, right, those are our 2 classes of materials. So now, we got a 50-50 chance. Which class of materials does von Mises work well? Yes, ductile. Thank you, John. Okay, so the ductile ones, right? And why is that? Well, the von Mises stress criterion is based on distortion energy. Okay? And so remember the whole thing, I put a block in the bottom of the ocean. Can anyone hear it scream? No, it's not like, the question is, will it fail? Right? And the answer is, if it's a ductile material, no way. Okay? Because there's no shear. Hydrostatic loading on the whole entire thing, no deformation, none of these fancy planes, sliding planes, whatever you want to call them. Okay? And so it's not going to fail. Now, you're like, wait a second. That means if I stick a pressure vessel underwater, it will not fail. Why is that reasoning false? If I stick a thin-walled pressure vessel underwater, well, you just told me that hydrostatic loading is not going to, not going to cause any problems. Why is that? Why am I wrong? There are multiple reasons why I'm wrong, but at least give me a couple. Yes. Person between Andrew and Alex. Your name is?
John.
John. Okay, John.
It's hollow.
It's hollow, right? Now, what if I say, let's take the hollow sphere out. Let's say it's a spherical pressure vessel. And now I pressurize it, just like, even I put it in tension. So one is, it's hollow so it can crush, and I can get buckling, right? Okay, if the and that comes down though to a difference between the internal pressure and the external pressure, and that's a problem where we don't like to focus on it in this class or in mechanics of materials, because we are only interested in when the pressure inside the vessel is higher than the pressure outside the vessel, which is good for most cases, right? But as you can imagine, you don't even have to imagine, you just look at what's happened in the last 5 years. Alright, if you take a hollow vessel and you put it deep underwater, bad things can happen. Okay? So, but let's just bring that spherical pressure vessel out of the water for a minute. And put it in the sky, in there. And we pressurize it inside. What are the stresses in a spherical pressure vessel? In a thin-walled spherical pressure vessel? Anyone remember? Yes, Alex.
Axial and circumferential.
Okay. So you're remembering? Yes. It's spherical though. Okay, so if it were cylindrical, right? You're absolutely right. You have the axial stress, which we call, okay, and you have the circumferential stress, or whoosh, there it is, right? All right. Now, in a spherical pressure vessel, it's completely symmetric, right? So then the two, I said it, we kind of think at a given point, right, you're thinking, okay, there are orthogonal stresses. What kind of stresses are these? Okay, just let's say you got two choices, shear or normal. They're normal stresses, okay? So wait, if I just have normal stresses, and it's a ductile material, which means that there has to be failure because of distortion, what's going on? Why does it fail? Anyone? Quadrant 4. Actually, quadrant 4, you've been very quiet. So why would it fail? I have a ductile material that's supposed to only fail because of shear, and I have these two normal stresses. Why does it fail? So, right, remember, we can even draw the nice little, right, we have the nice little sphere. That's not really a good sphere. Oh, that's a horrible sphere. Right, but let's just say that I've got like a stress that direction, I got a stress that direction, and actually they should be the same. And it turns out that that stress will be the same state of stress as that stress. Will be the same state of stress as that stress, right? Because it's all radially symmetric. Right? So what's going on? Why would a ductile material fail in this circumstance? I've got these equal stresses in orthogonal directions. What's going on? Yes, John in the middle.
Since the stresses on the outside that aren't equal to the ones on the inside.
The what?
The stresses on the outside aren't equal to the ones on the inside.
Okay, I mean, it's a thin-walled vessel, so, right, we said that there's not really much of a change, right, in the thickness, okay, with these stresses. There is something, though, to what you're saying. Yes, Rohan.
Does it depend on the coordinate system?
Well, I mean, does the pressure vessel care which coordinate system I'm using? My calculations will depend on it, right? What's going on, though? Why fundamentally is a ductile material going to fail at a certain level of inside pressure? Yes, go for it, Alex.
Well, isn't it because, because of what I'm saying, if the outside pressure is more than the inside pressure, isn't that pressure difference going to slowly, eat away, the material strength of it, and that'll cause it to, deform into, maybe you won't, see it as much, but, internally until it just...
Okay, yeah, I mean, I agree that you could have some micro cracks over time. That's a fatigue thing, which is also a GMC topic, right? So fatigue can lead, yes, to cracks forming and everything, but I suggest I'm cycling it. Okay. Any other ideas? This is kind of a little bit of a brain teaser. Okay, maybe not. I just told you that I need distortion, which means I need shear stress. But the way we've described the state of stress, I haven't said anything about shear stress. Now I'm giving you a hint. So where's that shear stress coming in? Yes.
Is it the way the material is held together?
Well, yes. I mean, ultimately, yes. Okay. I'm telling you, though, there's shear stress. Now I'm being so blatant. Where is that shear stress coming from?
Is it just internal?
Oh, of course it's internal. It better be internal. That's what the stress is.
Doesn't pure normal stress can also be converted to shear stress?
Oh, yes. And why is that the case?
The only thing I remember is ductile materials, they fail in 45 degrees.
Ooh, yes. In fact, I'm with you. Okay, we're going to jump through this real quick. I'll come back to this. Do you remember this? No, that's a no. I got some no's. I don't remember this, okay? Normal stress, zero stress, normal. Zero stress, normal. Okay? So then, if I take a perspective, in this case, if I use more circle, remember, I have to draw the circle, okay? And I can get the tau max. Okay? Now, this comes out, this is just more circle. I jumped over the step where we did remember when we did the slicing of the triangle? When we took an element, we sliced it, and we had the triangle, and I forced you, if you were taking the class with me, to know how to do equilibrium on that triangle. And if you did not do the equilibrium derivation on the exam, you didn't get full credit. Does anyone remember that? Okay, no. Okay, good. I'm glad we haven't started. Okay, but so the point is that in the pressure, so just like from what we were saying here, right? We have normal stress in this direction, but if you rotate the element 45 degrees, you can figure out what the pure shear is. Actually, it's not pure shear. I just misspoke. you can figure out what the shear stress components are. Okay? Because right? And then the Mohr circle, right, would tell us that, okay, that maximum shear stress is going to be what? Half of the normal stress that I've got. And I still have components, okay, of normal stresses as well. One being positive, both being positive, okay, sorry, I'm speaking poorly. Both being positive, and that is also half of the normal stress, right? So what happens, right, you've got this element like this, and let's just say this is the sigma 1, right? That's the principal stress. And then when we go to 45 degrees, okay, so we've rotated 45 degrees, that means that we went to this, we went a 45 rotation this direction is equal to the 45 degree, remember, rotation in this direction? So now the normal stresses are half like that. Is that looking familiar? And the shear stresses, right, those tals are also half. Does this sound familiar? Okay. So this depiction is explaining why if I have a pressure vessel and I have normal stresses in two directions, that third direction is the killer, folks. There's no stress in that direction. There's no normal stress through the material. It's very thin, right? If I think I even have some slides, and I like the explanation from David Roylance that talks about how it's thin, and where is it? Here you go. This is plane strain. We'll go back to this. All right, here we go. Remember? For a pressure vessel, remember that we have a sigma 1 and sigma 2. This is cylindrical pressure vessel, right? But what about sigma 3, or the stress in the normal direction of the surface? Okay, on the inside we could say it's sigma 3 is equal to P, right? And remember, this is the sigma 1 and sigma 2 are like 5 to 10 times larger than what the internal pressure is, or the pressure difference, better said, between the inside and the outside. So we can say that the sigma 3, like there's some pressure on the inside, but then it goes to essentially 0 on the outside, and we can say that there's essentially no sigma 3. Okay, does this sound familiar at all? Okay, so because that sigma 3 is equal to 0, then you have distortion. You're pulling in these two directions and not pulling in this direction. If I were pulling in this direction, then I just could have like really nice volumetric, like everything's hydrostatic. Okay. But because it's 0 in that direction, I get distortion. All right, so I hope I didn't waste your time. The point is that, again, we can create pretty pictures with finite element analysis. Nonetheless, we want to get around some base cases that are going to leverage what we've learned in mechanics. Yes?
So you start off in a state with a bunch of normal stress.
Okay, or 3 normal stresses, or 2 normal stresses, yes.
So you use Mohr circle.
Yes.
And find out that, there's a max shear stress here.
Yes.
What is the physical significance of doing that? Yeah, it just feels like, I can take any state of stress and just spin it around. Now I have shear stress.
Well, and so so yes, I mean, you've said it kind of nicely that for ductile materials, we said there were 2 primary criteria. One is maximum shear stress. That was the Tresca criteria. Okay? And the other is the von Mises, right? And so they are similar, right? You remember we said, you can compare like this, you can use the Tresca or you can use the von Mises. Von Mises is actually a little bit more aggressive, right? The envelope, if you remember, the sigma 1, sigma 2 plots was a little bit larger. They're both, though, kind of based on the idea that failure in these ductile materials is because of sliding planes, right? Shear stress is going to be associated with a shear strain, right? And if you think about a shear strain, that is two planes sliding against each other. Okay. Now, actually, we kind of do it like with this little diamond-like thing, all right? And they're kind of like this in some sense, but it's because these materials fail as the atoms or as the molecules are sliding over each other. The ductile ones. The brittle ones, they fail because you're just trying to. That's maximum normal stress theory, if you recall, right? That's because the atoms you try to pull them apart from each other, and so it's really the bond energy in those directions. Did that kind of answer your question?
I think what confuses me is that initially you're saying there's no shear stress.
Oh, there's shear stress.
So then, why is it not in our initial stress state?
This is a very good question. It's not because it's in that particular coordinate system. Okay? So remember, I can rotate tensors. Right? The whole thing with a tensor is that it preserves the overall information, okay, of the state of stress or whatever it is. But as you rotate it, it then says, oh, actually that normal stress that you have here, I'm going to have it poke out in a shear stress component.
And what would be the significance of that rotation?
The significance of the rotation? Well, that goes back to I've got to take a cube, right, and I've got to take a plane, and I take it at some angle, and I have to satisfy equilibrium. Okay? So ultimately, these rotations are about satisfying equilibrium, but just from a different coordinate system. That's very good. So yeah, but you need all three. It's not to say that there's no shear stress, right? It's to say that when I look at the entire state of stress, the sigma 1, sigma 2, sigma 3, or the sigma, or better said, sigma x, sigma y, sigma z, the shear stress is tau x, y, tau x, z, tau y, z. When I look at all those stresses, yeah, they have all the information, and now I got to figure out the orientation, essentially, that tells me, okay, what is the magnitude, what's the absolute maximum shear stress? And if I really want to do it, I want to say, oh, well, in which direction, like which sliding plane is going to be the plane that causes the failure, then I have to do additional work to figure out, okay, that is the plane that I can define by appropriate rotations. Okay. Which is not something that we really emphasize in 3D. In 2D, though, we can do it. Okay. In 2D, we can do it, right? Because remember, we had, this is how much theta S you have to have to be able to get to that state. Good. All right, so let's see. This has been a nice. Hopefully, I enjoy talking to myself sometimes. I enjoy talking with you, and thank you for cooperating. Okay, so we're going backwards, by the way. Okay, now, oops, now I'm going forwards. I should just use the keyboard. Okay. Oh, now, maybe you saw it, maybe you didn't. Well, we're solving our problems in mechanics using statics. There were three pillars, three categories that we like draw two lines on a piece of paper, and there were three pillars. Do you remember what those three pillars are for solving a mechanics problem? One of them is there. It's written in letters already. So equilibrium, right? And that we spent a whole semester doing statics. Okay. But what's the problem with only using statics to figure out stresses? Yes, Rishi.
You need to go.
Okay, so here everything is static, right? So
Like the moments.
Huh?
The moments.
Moments. Okay, momentum and moments are different. So yeah, you had to involve moments, but I'm going to say that the equilibrium that we're talking about, and maybe I should change it, it's a study of forces and equilibrium parameters. Equilibrium does in fact include the moments. Okay. So what's the what else do we need in order to be able to calculate stresses and strains?
Geometry.
Yes. So we need a geometry, right? So geometric compatibility. In particular, we need to know something about boundary conditions. Okay. And we sometimes need to say, okay, remember this displacement here is going to be equal to 0. This displacement is going to be equal not to 0. These displacements here and here, they're going to add up to equal to 0. Remember all of that? Okay. So that's all under geometric compatibility. How do we go from displacements from between displacements and equilibrium though? That's the third pillar. What was that category called? Any remembrances? So we've got two. We've got equilibrium and we've got geometric compatibility. What's the third one? Yes, okay, all right, yes, that's a good time to pull that out, all right? So elastic modulus is part of what we would consider an important set of, or important variable, important parameter in the constitutive relationships. Okay. So the constitutive relationships are what relate the force and the deformation to each other. Okay, so Hooke's law is a constitutive equation. Okay, sigma equals E epsilon, or F equals K delta. That is going to be, those are essentially constitutive equations that allow us then to solve for problems that you cannot get along. You can't solve necessarily. Well, you definitely can't solve for strains. Okay, but for those, especially for those indeterminate problems, right? Where it's like, hey, I've got equilibrium only gives me a couple sets of equations, and I've got 3 unknowns. Okay, so how do I do it? I need additional equations. I need another equation. And so the constitutive equations and the geometric compatibility help us out. Okay, so these are the 3 pillars: equilibrium, geometric compatibility, constitutive equations. If you look at the theory for, or some ways of describing the theory for finite element analysis, look at this. It's nasty. And again, this is an impressionist perspective. The 3 categories are equilibrium, geometric compatibility, and constitutive relationships. Okay. So even when you, and so these are the differential equations, the PDEs that are being solved. Okay. But even when you set up your problem, now when you put it in simulation, you're kind of like, oh, I have to put some forces on this thing. Oh, that would be under equilibrium, or I put some moments, right? And I know that it's not going to deform, or I know it's not going to move. All right, when I do this, or it can move. I mean, you know, it's not going to accelerate. It's not going to, like, this thing has got to be fixed somewhere. We'll come back to that point in a little bit. I am going to be interested in what's happening with the geometry. Okay, that's great. I'm going to be putting boundary conditions. That's great. That's all geometry. And then I'm going to be interested in calculating the strain and the stress. Okay, so then I've got my constitutive relationships. So we have kind of this idea that all these things are coupled together. Now, are these equations as straightforward and simple as the heat equation? No. Okay? And that's maybe why you're like, well, why didn't we do this earlier? Well, the reason we did it later, and I like how Professor Singer has things set up, is we essentially said, hey, we're going to do particles, then we're going to do finite difference, right? I mean, and then with finite difference, you could like solve second order partial differential equations, and you could do the local oxygen, and you could do that with a heat equation. But we didn't, and then we did finite element, and we said, oh, well now we can do finite element with the heat equation. Right? But we didn't jump right into, let's do the mechanics problems, okay, using the finite element. But that's what we're doing now. So just like we did with the heat equation, and just like the computer is doing for us, essentially in these static problems, we have a forcing vector that we were literally calling F, okay, for forces, and we have some output. In that case, it was temperature, right? But maybe we're interested in the state of stress, okay, throughout the object, okay, and that's going to be related to the K matrix, all right. And if maybe a better analogy would be, I have some delta, all right, which is going to say the deformation of the object is equal to the inverse of K times F, right, or F equals K delta. And that's what we're essentially having the finite elements also do for us. And just like we described before, there are these test or trial functions or basis functions that we kind of set up to kind of go ahead and gradually get us to the state of strain, the state of stress, the state of deformation of this object. And there are different types of elements that can be used. The more nodes you have, okay, the more curvature an individual element could have. Like if it's just the triangle, it has boom, 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 3 nodes on the corners, then that's going to be, kind of planar, at least that element, right? But then you have its next door element that can be also planar, right? And so you can have kind of this interesting shape or sets of shapes that you just build with triangular elements. But you could add extra nodes to the sides of those triangles, and then now you have kind of these more interesting types of shapes, like you see here, where there are nodes on multiple sides, and not just, so every element isn't just kind of a linear gradient across it. Every element can have its kind of own curvature and try to capture the detail more faithfully. Okay? And so again, this is just an impressionist perspective, okay, of kind of some of the equations that are used, all right, for a finite element. But you can see that as epsilon equals BQ, this sigma is equal to something else, right? Because some constitutive relationships, and this is what the finite element is doing to solve. Now, when we think about the objects we're going to simulate in finite element, we can think in terms of thin ones, which are states of what we would consider to be plane stress, or we can think of them in terms of thick ones, right? Which is what we consider to be states of plane strain. And we can think of them in between as well. Okay, so that's a very nice aspect of being able to do a real geometry and be able to do a real 3D geometry, is that the world is not split into just very thick plates and very thin sheets. Right? It's actually a combination of the two. So when we think about symmetries, we've discussed some of the symmetries in particle dynamics, we've discussed symmetries in fluid, we've discussed symmetries in heat, right? There's actually interesting symmetry in structural mechanics, which we don't use very often, but that is essentially of, like if I say, oh, this is a solid structure, and I want to kind of symmetrize it, if you could say split it down the middle, you can think, oh, well, it's almost like I have a frictionless boundary condition between the two, okay, as this slides up. So this is something that Professor Steve likes to emphasize, and I think it's a little abstract, but that's kind of one additional way of applying symmetry to structural mechanics. Okay, so let's do some let's do some basic examples, all right? And we'll cover buckling, actually, we'll cover buckling next time. And not today, all right, but the next time. And today we're gonna focus more on the static loading and also static thermal loading, and just showing you how it's set up in Ansys. So we're going to use, we talked about failure criterion already. We're going to use a bar under tension, a cantilevered beam, and a bar under temperature, thermal expansion. Okay. This bar we're going to start with is kind of like a thin sheet. All right. And while I'm talking, let's go ahead and bring up Workbench. There we go. So it can load. We're going to have it have a thickness of just a half centimeter, so 5 millimeters. And we're going to have it have a span across the top of 3 centimeters, and we're going to have it be 15 centimeters long. Okay. And then we're going to apply a load normally, so kind of pulling this thing apart and being able to look at what the normal stresses are, and also be able to look at the von Mises stresses, the equivalent stresses, and kind of get some ideas and compare it to theory. So to get started here, we're going to come down to, here it is, static structural, and we put it in. And this time we can do a couple things. Let's start with the engineering data here. So this is stainless steel, but let's go ahead and say we want to, and that's, their default there. Let's just call this generic steel as our material element. And you see as our material that we're going to be using. And you see it's empty. We talked about this now a few minutes ago. What are some of the material properties? What are the basic material properties that we want to use to define our material for finite element? Like what kind of quantities, what kind of material properties should we drag in there? Huh? Yeah, so elastic modulus would be a good one, right? So we can come over here to isotropic elasticity, and we can drag it over to this property thing, and boom. All right, now we called it steel. So what do you want to put in for the elastic modulus? Anyone? Elastic modulus of steel? Sure. We can put in 210 if you want. 200, 210. Sounds good. What's? Yes. Your GPA depends on knowing this. All right? So 210 gigapascals. All right? So that's E to the 9. Okay? And Poisson's ratio, 0.3 is not bad. Okay? And it's already done some other calculations for us. Here, we can also put in a density, although it doesn't really, we don't care that much, but the density for steel is, anyone? What's the density of steel? No idea. Okay, what's the density of water? 1,000 watts. Okay, is steel more dense or less dense than water? Good. All right. So now we have a lower limit. All right. 1,000 being kilograms per meter cubed. All right. Yes. 7,000. That's a good guess that the internet, I think, just told you the answer, right? So 7,850 kilograms per meter cubed. Now, is aluminum less dense or more dense? How much? You don't know. That's okay, right? Well, is it okay? So aluminum is around 2,700 kilograms per meter cubed. What are some of the most dense solids? What are their densities like? Huh?
Lead.
Okay, so lead is pretty dense. That is going to be probably around 10,000 kilograms per meter cubed. Yes. Tungsten's also more dense. That's probably close to 18,000. Okay. 19,000. Gold. You know, gold is like around 19 or 20,000 kilograms per meter cubed. Simple gold. Platinum, also pretty dense. Okay. Gold is a popular quantity right now, if anyone's looking at what's going on in the world. But anyway, so yeah, so those are just some general ideas. Plutonium, also pretty dense. But yeah, it's kind of, you know, we have our elastic moduli, and even though we don't think about density too much, it's pretty good to have an idea. I asked the other class this same question. If you go into the machine shop, actually you don't have to go into the machine shop. If someone hands you a sheet of metal and says, is this aluminum or steel? Can you tell the difference just by holding it? You can. How can you tell the difference?
Aluminum feels a little lighter.
Yeah, it feels a whole lot lighter, right? Okay. And it's not because you took it and you hit your head with it, right? Although that's another way you can probably figure out, you know, which one is which too, if they're the same thickness. Because the elastic modulus is going to be a third in the aluminum case of the steel. Anyway, okay, so we've got material properties. Since we're going to do a thermal problem as well, let me see, where is it? We can also put in this. Yeah, this is fine. We're going to put in the thermal expansion, okay? And that's usually like 10 to the minus 6 or so. 10 times, it's 10 times 10 to the minus 6, okay? Or 12 times 10 to the minus 6. We're going to use 6 just because that's what I did before, okay? So 6 e to the minus 6. And of course, if I wanted the volumetric coefficient of thermal expansion, it would be, if I have 6 times 10 to the minus 6, what is it going to be if it's a volumetric coefficient of thermal expansion? Oh, here's a hint. Yes? Yes, right, factor of 3. Okay, don't cube it. Just multiply by 3. And you can go ahead and look back at your mechanics and materials notes to be able to figure that out. All right. So, I think we've got our material properties set. Let's go ahead. Woohoo! We get to leave it in 3D. All right. We're going to go ahead, right click, and we're going to do new space claim geometry, and we'll wait. Did anyone have fun with Design Modeler? Takes more RAM, doesn't it? A little bit slower. I tried to get the airfoil thing to work in space claim. I could not. I failed. So instead, I followed what other people did in Design Modeler. But if you all have success with space claim and importing your airfoil geometries, feel free to post a video, and I will like it for you. Okay. Maybe someone already has, right? Okay, but okay, so we're waiting for space claim to start up. What's nice in the static structure model is that, or this module, is that we will be able to write a systems analysis system. Is that in the next step when we do the modeling, the results will appear in the same window. It's not like Fluent. Well, Fluent does that too. I'm sorry. The results that we're interested in will appear in the same app. I don't even know what to say. Same sub-software thingamabobber window that we do the meshing. So we'll be able to do meshing and get the results at the same time. Okay, so here we are. waiting. All right. And we can go ahead and we'll do the top down. We'll look. Okay. And in this case, if you want, you can change the units that we're interested in using. So you could come over here to units, and we're in millimeters for now. Okay? And that will be suitable for the geometry, because the geometry we're interested in is not crazy. All right, 15 centimeters, so that's 150 centimeters this way, and 3 centimeters this way, or 30 millimeters this way, and then it's got a thickness of 5 millimeters. We're going to draw the top-down perspective, and then pull this this surface up. So we'll just put a rectangle in, and we'll click here. Oh, did I not click this? Maybe I had to click. Sorry, yeah, to click this first, and then now I do the rectangle. Okay, and what did we say? We said it's going to be 150. So 150, and then tab, and it's going to be 30. And I hit enter. Okay, and now we have this geometry. This is one of those nice opportunities where you do hit the end sketch. Sometimes you you just close the space claim. I know it's confusing. Okay, and then I can pull this up a little bit. I click on the pool's already selected, but I'm going to do a pool. I see this arrow here. I hold my left button down, and it comes up with this thingy. All right, and while my right hand is, or while my left click is still engaged, I type in 5. Okay, hit enter. Now it's 5 millimeters. Hold, it's just like, yeah, you got it. All right, so now I've got my structure. That is what I want. I just go and I close, don't do anything else, and we come back into the workbench, and we can go ahead and start the modeling. And the modeling will be two things, right? We're going to do the meshing, and we're going to do the putting of the we're describing boundary conditions. Now, when we have this type of picture, it looks really nice. You know, you have these forces on either side, and it's just magically in space. One of the things we want to take away from today, if anything, you're like, maybe nothing, but take my word for it. When you're doing static structural analysis, this is not using the explicit dynamics, all right, that Ansys has for you. But when you do these static problems, you want to make sure you have something anchored to the ground. Okay? You can't just put one force here and the exact same force here and have it solve for you. It will not do that. Okay? It needs to have something anchored. All right? Even though it's balanced in terms of force, it's not really any type of little thing, right, off. It's just going to not. It'll tell you it will not solve. Okay. So we come over here and we see that we have a geometry, and we have this solid. Okay, that's good. We have this material, and we see, oh, there's still structural steel. I think I made a boo-boo. All right, because what I really want to do is I want my generic steel to be assigned. Okay, so when I look at this, okay, I can come over here and I say, no, I didn't really want. I was just kidding. I actually want generic steel. Okay, so make sure you change that. Not that I've ever made that mistake. Actually, if you go back here, okay, to the workbench, you can come in here, and what I should have done, I should have right-clicked, and I should have used this steel, my generic steel, as the default solid material. Okay, but I didn't do that. I forgot. So anyway, making the correction there. For the mesh, all right, we'll go ahead and we'll insert sizing. Okay, and we'll do a geometry. So we're gonna, well, let's select the body. Let's select the whole thing. Okay, and then we're going to change the element size. And if I do like 5 millimeters, okay, and I do generate, and then I come back and I click on mesh. That's a really nice regular mesh, but it actually is probably not the greatest for describing what's happening. Remember, my beam is 5 millimeters thick. All right, so that's, it's just one element thick. So I can come back here. Let's do something a little bit different, and we'll put in 5. Let's put in like 2 millimeters. 2. Whoa, that's microns. No, 2 millimeters. Okay. So let's come over here. Let's change this. Okay, we're going to change ourselves to be looking at millimeters. Okay, so now let's do 2 millimeters like that. All right, and let's go ahead and we'll generate. Okay, and then we'll click on the mesh again. That's pretty good mesh. Okay, and yeah, there's a little bit of art, and I'm not showing convergence in this case, right? But if you wanted to show convergence, right, you would nicely say, oh, here was one. This is when I had 100 elements, right? When I used the mesh size of whatever I used. Okay, this is when I had 1,000 elements, right? And you show that the values stop changing, and whatever value would be of interest, maybe a stress. Okay, so now what do we need to do? Well, we need to add some boundary conditions. So maybe the first thing to do is let's just go ahead and add a force to the right surface. So this is a force, and it's for a face. All right, and I'm going to select that face right there, and then I'm going to come over here, and I'm actually going to break it into components. You could break it, you could use it as it was, but we're going to break it into components. Now it says there's no selection selected, so now I've selected it, and we're going to do it in the X direction. And in the problem at hand, we're saying that we're applying 10,000 newtons. That's a lot of force. Okay, that's a lot of force. Foreshadowing, if this were a buckling problem and I applied it in compression, I would have some other issues, right? Because this looks like kind of thin-zy, flimsy, right? But here I'm just going to put 10,000 newtons in the X direction, just like that. Now, what we said before is that we can't just put another force on this side. So for now, what we're going to do, because it seems mathematically, or in equilibrium, it seems like it should be balanced, but in mechanics, that's not giving this a solid base. So what we're going to do here is we're going to use a fixed support on this side, just like that, and we apply it, okay, and we should be good. But my solution doesn't have any interesting results. So we're going to introduce some things like, let's look at the normal stress. All right, this problem is going to be a good one for normal stress. Let's look at, sorry, let's not do that there. Here, we're going to look at, let's look at the strain. You can look at normal strain. Let's look at, if it's a ductile material, which it's steel, so it's a good chance it's ductile. Let's look at the equivalent Voronoi stress. Okay. Let's look at the deformation. Let's look at the total deformation. Okay. And let's go ahead and run this thing. So now we hit solve. And it's thinking. What do you expect? So, well, what do we expect to have? If we did this right, force divided by the span times the thickness, that's the B and the H, we expect that it will tell us that we have a stress of 67 megapascals. That's a normal stress. Okay? So let's see what happens. Okay? Well, this is the deformation. So the deformation, what's going on? Why is it not all 67 mega? Well, it's because deformation, right? It's progressing. As it moves along, it gets larger and larger. And that's what I'm selected here. Let's look at the normal stress. Okay, and now the normal stress, if I hit a probe up here, and I click, oh yeah, 66.7. And what are these units? Megapascals. That's good. What's going on here though? Look at this, 77. But it's not happening over here. Remember the force is on this side? What is going on over here? What's going on? Why is this not all nice and perfect on the left side?
That's the fixed end, right?
It's a fixed end, yes. So what's happening? Yeah, Isha? What's that? Yeah, support reactions. And remember, this material has a Poisson's ratio, right? So when I pull in this direction, on the right, this is actually extending, deformation this way, right? But it's actually also contracting in those two directions. This fixed side does not allow it to contract in those two directions. And so you have this abnormal, well, it's not abnormal, it's just this is the pattern that you get when you have this fixed end. So if I want to make it look very like a textbook, okay, what can I do? What can I do? I want to see 100% uniform stress across this entire structure. What do I do to do that? How do I do that? Any ideas? Well, what's causing the problem? What's causing the problem is I have completely fixed, right? So maybe I don't want completely fixed, right? Because if I have completely fixed, then when it tries to contract in those two directions, it can't do that. So what do? Well, first, let's just go ahead and suppress that. Okay? Now, we said that we needed to have something fixed. Let's just pick a point now. Let's just pick a point that we can fix. So we're going to do a fixed support. And in this case, we're just going to come over here and we're going to do a vertex. And I select that. I hit apply. Now, is that enough? No. What else should we probably do? What do we really want to constrain? What do we need to make sure does not go anywhere? Or which direction do we don't want it to go? We're running out of time, so without pestering you too much, we want to make sure that the displacement in the x direction is fixed, but the displacements in the orthogonal directions is free or fluid or able to just contract as we like. So what we do is we add a displacement constraint. See this? We click on this. Oh, actually, I guess I need this face. We click on this face, apply it, and you see it says x component free, y component, z component free. So it's doing nothing until we say it's 0. We're not going to allow it to move in the x direction, but we will allow that surface to contract or expand, whatever it wants to do in the y and the z directions. So now we go ahead and we click solve. Oh, no. So I did something not so good, I guess. Force is still there. Fixed support. One vertex. Displacement. That face. This force. Well, this is embarrassing. 0. Let me suppress. I'm going to do, instead I'm going to use, actually I'm going to do, no, that shouldn't do it. It should have just worked. See, this is where it should be 0. Wait, suppressed? Why is this suppressed? No. Displacement, okay. That geometry, this face, this vertex. Suppress, no. Okay, well this should have worked, and I'm not sure why it's not working. Fixed. No, now I've got too many. These are suppressed. Where did I put it? Where did I put it? Did I put it? Yeah, that's a fine spot to put it. Okay. Well, I'm having a brain freeze. Okay. But that should, and if you look at the previous video, you can get it to be completely perfect not perfect, but completely uniform. Okay? Well, we're out of time. And that's a downer of a note to end on. We'll come back to it. Let me just save this. Well, I'll save in a second. Let's go ahead and we'll do the attendance, and you'll be on your merry way. Thank you, everybody.